The Smithsonian Faculty Fellowship program represents a rewarding academic professional development opportunity for faculty at Montgomery College. The fellowships are a product of a unique collaboration between Montgomery College and the Smithsonian Center for Learning and Digital Access. It's the first of its kind between the Smithsonian Institution and a community college.
Craig Benson is a professor of chemistry at Montgomery College, Rockville, where he teaches Principles of Chemistry 1 and Chemistry in Society. Prior to arriving at MC, Benson was a researcher at NASA Goddard Space Flight Center using the GEOS-5 Global Climate Model. Craig recently completed a sustainability-focused learning community, Preserving the Blue Marble. He has also led 2 MC-sponsored study abroad trips to Iceland, in which students studied the geology of Iceland, the effects of global climate change, and the implementation and benefits of geothermal and hydroelectric power.
Let me share my screen with you while I present my Smithsonian project for this semester called Ancient Carbon in Modern Times. Now, the original plan for this Smithsonian project was to develop context for our Principles of Chemistry 1 class, Chem 131. It's a very content-heavy class where students learn a lot of information in a very short time. And that information is often presented with minimal context, and so students have a very difficult time grasping the real-world implications of what they're learning. So my idea was to bring climate change concepts into Chem 131 and connect that with the lessons they were learning during the classroom. And then, using the Smithsonian resources, they could learn more deeply about climate change, and then we would cap it off with a trip to the Deep Time exhibit at the Smithsonian Museum of Natural History, where students would appreciate the deep time scales involved. At the Deep Time exhibit, they could see the tens of millions of years it would take to form fossil fuels that we then dig out and burn in a very short time. And so it would really give them that visceral feel for the global implications of climate change. And that's why the project is called Ancient Carbon in Modern Times, because we have ancient carbon from fossil fuels that we're digging out and using today, despite the fact that it's been underground for tens of millions of years. So that's the plan. And then March happened. And in March, of course, the Smithsonian closed down and Montgomery College closed down. We went to emergency remote instruction, and we are still in remote instruction. And therefore, I could not bring my students to the Smithsonian in order for them to get this experience. So after the requisite bit of mourning, I had to figure out, how do we have a Smithsonian section without a Smithsonian visit? And so I had a plan in 3 parts. That first part is, still give them that focus on climate change. We can go into the classroom, still apply the lessons to climate change. It's just that the capstone presentation, the capstone event at the end can't be a Smithsonian visit, but that capstone event can still have a lot of those same components. One of which is to maintain the focus, the essence of the Deep Time exhibit. If I wanted them to have a sense of those deep time scales, then I need a capstone project that will give them those deep time scales, that essence of deep time, and link it to the Smithsonian resources. And then the third part is I really wanted to bring them to the museum, but just because we can't go to a museum doesn't mean they can't have some aspect of museum learning, some museum visitor experience that is preserved. So while I couldn't bring them there, they could bring the museum to me and to one another. So more on that later. So then the first part was focusing on climate change. And for most of the semester, the entire semester really up until that capstone project, we were able to do so. I rewrote all of the group work and all of the guided inquiry-based assignments that I use in my classroom around the concept of climate change. So I just gave one example here of the type of work that we did in the class. This was a carbon dating worksheet in which students would analyze the isotopic ratio composition of the carbon in the atmosphere. as they were learning about isotopic compositions and what isotopes are, they could apply this to the carbon in the atmosphere and see that that isotope ratio is changing because as we introduce ancient carbon into the atmosphere, that carbon is getting older. Older carbon has a different isotopic ratio than carbon that is generated in the carbon cycle during modern times. And so as that isotopic ratio changes, it's evidence that we're putting ancient carbon into the atmosphere. So that's one example of a type of assignment they were able to do in the classroom with one another and then have a discussion about. So then, we prepared them throughout the semester. And then for the capstone project, we used the Museum of Natural History's interactive leaf margin analysis. Using that interactive leaf margin analysis, which is a fantastic simulation that a digital exhibit made by the Smithsonian, students were able to take a look at the rate of heating during the PETM and compare it to modern day rates. So I know the question you might have, what is the PETM? The PETM is the Paleocene-Eocene thermal maximum. So if you take a look at this plot, this is a time series of global temperatures going back nearly 70 million years. Clearly, we didn't have thermometers 70 million years ago, which is why we can use proxy data, isotopic ratios of oxygen, which are highly correlated with temperature. And based on that proxy data, we can infer what the temperature is. Now, you can see a big spike in between the Paleocene and Eocene eras. That is a Paleocene-Eocene thermal maximum. At that time, there was a rapid increase in temperature and a change of several degrees Celsius. Now, people who disavow anthropogenic climate change sometimes point to the PETM and say, well, we have had rapid temperature changes before, therefore, what we're seeing now is nothing more than natural variability. So I challenge the students to evaluate that claim. What are the similarities between the PETM and today? And what are some of the differences? Is that heating rate really analogous to the heating rate of today? So that leaf margin analysis was able to help them out. Now, the way the leaf margin analysis works is there were two separate dig sites that were separated by 100,000 years. And within those dig sites were a number of leaf fossils. Now, if you have ridges on your leaf, then you are more prone to evaporating water from that leaf, but you're able to start photosynthesis earlier because you have an additional extra surface area, which means at colder temperatures, there's more of a selection for ridged leaves because you can start that photosynthesis, but you don't really have to worry as much about water vapor loss. Whereas at high temperatures, you don't want to have those ridged leaves. You want to have smooth leaves, minimizing the surface area and reducing water loss. So by looking at the different fossils of leaves and whether they're ridged or not, students can use that as proxy data for the temperature and get a good sense of what the temperature was like during each of those sites. Now, if they have a temperature and a time, which they do, they're separated by 100,000 years, they have a rate. It's not a very precise number. There's certainly a lot of variability, but they have some vague sense of the temperature change per year. They have a rate of temperature change. They can also get that from modern times. They went to NASA's website, downloaded the most current data set for global average temperatures. Global average temperatures, it's not a linear curve, but again, they can get an estimate by taking that last 40 years from 1980 to today and approximating a linear increase. They downloaded that data set, did a linear curve fit, found the approximate rate of change of the temperature today, and compared that to the PETM. Their findings were that if that average temperature from the PETM through the leaf margin analysis is correct, and their linear curve fit is correct, and again, they're both estimates, but they're robust enough that they should be able to make that comparison. They found that current heating rates are 300 to 400 times greater than that during the PETM. So it's not really a perfect analogy. It's the greatest temperature spike in the record, so it's as close as anything else we've gotten, but you can't say that modern heating rates are like those ancient heating rates, because the heating rates right now are so much greater because we're having such an outsized influence on the climate. So that was the first part of their capstone project. The second part was trying to replicate that museum experience. So if we went to the Deep Time exhibit, the curators would have been able to show them exhibits that brings real world data into something that's very digestible for people who haven't studied that real world data. And I wanted them to be able to do that. They did this analysis, so then they need to be able to share it with others. And communication is a very important part of studying science, for one thing, but another thing that would allow them to both imagine what that museum experience would have been like and to share it with one another. We're not great at visualizing large numbers, so I challenged the students to determine some way of expressing some aspect of climate change and these large magnitudes that they were dealing with to someone who hadn't done a study like this. They got their exhibit together, they shared it on a Blackboard wiki so that everyone was able to see it, and then one day we went on a virtual tour of their virtual museum. I wanted to highlight a couple of examples. This is something that one of my students did, showing how the heating rates were different between now and the PETM. He likened it to having an ice cube and trying to melt that ice cube by holding it in your palm on a brisk day and walking out, versus taking it and putting it in a microwave and heating it up in a microwave. Both ways you get a puddle of water, but one way is much, much faster. And you might have some experience with being outside on a brisk day and heating things in a microwave. So that's the kind of thing that you can take that data and present it in a way that makes sense to people who didn't study that data in the real world. A couple other people went the way of more of an artistic representation. So the one over here on the left is, clearly a cry for help for the planet. But what I found interesting about this is that the temperature of the Earth corresponds to the temperature of the colors in the graphic. So all the way on the left, when it starts out cooler, if you read it left to right, you have very deep, dark colors representing that the Earth, was a lot cooler many years ago than it is now. As you read it left to right, that temperature becomes warmer until you see that graphic of the forest fire all the way there on the right. So even though it's more artistic, it really hides some scientific data behind it and presents it in a very visual way. The one on the right I really enjoyed also. This one is sort of a graphical representation of how climate change works. You have your greenhouse gases, NO2, CO2, CH4, and H2O, that trap infrared radiation, causing the molecules to vibrate and trapping heat. Well, that is proportional to the concentration of those gases. So as you read that figure left to right, you can see that the concentration of those gases continually goes up, the shade gets darker and darker, and climate change increases. So it's a way of showing that increasing that carbon dioxide or that methane will lead to more climate change. So I really liked both of those. I know I'm running a little short on time. I want to finish off with a couple of student quotes. Students found the climate change focus interesting and scary, and didn't realize there were as many different aspects to climate change as there were. That middle quote was fantastic for the Smithsonian section, that they enjoyed how the Smithsonian makes complicated information and new topics more interesting and easier to learn about. And they also really liked that virtual museum that makes them think and show their creativity. Thank you very much to Philippa Rappaport and everyone at the Smithsonian. We had a really great time hearing about all of these exhibits, right from the horse's mouth, so to speak. And thank you very much for sharing your expertise with us. Sarah Ducey, Mimi Mann, and Denise Dewhurst were fantastic leaders for this. Thank you to my cohort for all the discussions and the really excellent year, and to my Dean, Jim Sneezek, and Chair Laura Anna for their support. And thank you for your attention.